So here we're going to be looking at finding the arc length using the arc length equation. And the arc length equation, when it's not parameterized, is given by this equation. It's the integral of 1 plus dy dx squared times dx. Now I want to give a little illustration of why this is the equation, because sometimes I don't want people to just memorize the equation and how I remember this. The way I think about it is, if I'm looking at the length of a segment here, okay, and I break it into little segments, and I want to find the length of each segment. If I just zoom in here, let's zoom in on this little segment here. Okay, it looks like a line, and if I were to imagine it were a line, and I were to say, well, I move over a dx, and a dx, and I move up a dy, then the length of this segment would be the square, by the Pythagorean theorem, dx squared plus dy squared. Now this is not a form we can do integrals in, so what we do is we factor out a dx squared, and I get 1 plus dy over dx. You know, there's a square of them. And then when I bring the dx squared out, it just becomes dx root 1 plus dy over dx squared. Okay, so that's the length of a little segment, and then I integrate over them. So that's how I remember the equation, this derivation of why this is the arc length. So we're going to go from 0 to 1. The square root of 1 plus dy dx, we have to square this. So dy dx, or y prime, the derivative, is 3 halves x to the 1 half. So it'd be 3 halves x to the 1 half squared. That's the integral from 0 to 1, square root of 1 plus 9/4 x dx. Now, I can simply do antiderivative of this, or I can do u substitution. U equals 1 plus 9/4 x if you want. So du is equal to 9/4 dx, or therefore 4/9 du is equal to dx. So then this becomes integral. Let's do bound conversion while we're at it. U of 0. When I plug in 0 into here, for x, I'm going to get 1. And u of 1 is equal to 1 plus 9/4, which is 13/4. So this is going to integrate from 1 to 13 over 4. Square root of u, du. Oh, I need a 4/9 times 4/9. So this is 4/9. This is u to the 1 half, so that's u to the 3 halves over 3 halves. From 1 to 13 over 4. And so this is 4/9 times flipping the 3 halves. I'm dividing by 3 halves, multiplied by 2/3. And then I'm doing 13/4 to the 3 halves minus 1 to the 3 halves. This is 8 over 27 times, I don't know, this is going to be 13 root 13 over square root of 4 is 2. 2 cubed is 8. 8 minus 1. I don't know, that's probably enough. Okay. So let's look at number 2 here. We're going to do the same thing. First we need to find dy dx. And I'm going to get this is equal to x squared minus 1 over 4x squared. And so when I compute this square root of 1 plus dy dx, this x squared minus 1 over 4x squared quantity squared, is going to be the square root of 1 plus, let's expand this out, this is going to be x to the 4th minus, when I do the inner term, it's going to be minus 1/4 just by itself, so it's minus 2 of those, minus 1 half, and then plus 1 over 16 x squared in the denominator like this. So then it becomes the square root. This 1 minus 1 half becomes positive 1 half. So it's going to be x to the 4th plus 1 half plus 1 over 16 x squared. And this I can then simplify, because kind of like this expansion turned into this becomes x squared plus 1 over 4x squared quantity squared. The square roots just cancel, becomes technically absolute value, but these are all positive terms. Technically I should say it's the, so when I do square root of something squared, it's the absolute value of x squared plus 4 over x squared. But because these are both positive terms, doesn't matter what x is, the absolute values can go away. And then, so now we're just going to integrate from 1 to 5 of this term. Because remember, we do the integral of this from 1 to 5. So this becomes x cubed over 3 minus 1 over 4x evaluated from 1 to 5. So I can get 5 cubed over 3 minus 1 over 20. All of that minus 1 over 3 minus 1 over 4. So let's do this. This is 125 over 3 minus 1 over 20 minus 1/3 plus 1/4. So this is going to be 124 over 3, combining these two. This is, what, 5 over 20? Yeah, this is 5 over 20 if I multiply everything by 5. And then minus 1 is minus 4 over 20. This does not divide evenly, and this becomes 1/5. So it's 124 over 3 minus 1/5. And I don't know what we're going to do. I mean, you know, whatever this is in the calculator. I don't know. This is going to be 620 minus 15 all over 15. What's that? Is that right? 520. 5 times 12 is 60. 60 plus 20. Or 600 plus 20. 620. 3. I'm going to multiply this, but it's not by 15 minus 3. So that becomes 617 over 15. Okay, there we go. All right. So now we're going to look at number 3 here. We're going to do kind of the same thing. Dy dx. The derivative of this is going to be 1/3 times 2/3 x plus 4 to the negative 1/3, right? And so when we do the square root of 1 plus this squared, this is 2/9, 2 over 9, x plus 4 to the negative 1/3 squared. This becomes square root of 1 plus 4 out of 81, x plus 4 to the negative 2/3. Right, when I square it, I multiply it. Now, there's going to be some substitutions we do. First of all, this x plus 4 is a little bit annoying. So let's kind of get rid of that, and let's see if that helps us convert this. So 4 out of 81, and this is really u to the 2/3 like this. Okay, and then we can add these two together. So this becomes 81 u to the 2/3 plus 4 over 81 u to the 2/3, right? It's one thing I could do. And then I could attempt to do another substitution, because this is kind of like, if I subtract 1, it'd be my, yeah, if I did this substitution, w, say, this is a good example of doing substitution multiple times. I'm not entirely sure where we're going to go with this, but dw would be 2/3 times 81 times 2/3 u to the negative 1/3 du, right? So this is 9 times 2, that's 18 u to the negative 1/3 du. Yeah, because I guess I haven't been keeping track. We're trying to do this integral, so to speak, right? This integral here. So I have this u to the negative 1/3, but in terms of w, I could, I kind of have it. Yeah, because if I pulled, so you see, if I pulled this part out, I have the square, like pull out this numerator, it's 81 u to the 2/3 plus 4. And then this is going to be, if I pulled it, just divided by the square root of 81 u to the 2/3, that's really, this part changes to 9 u to the 1/3. And that's kind of what I have here on the denominator. So this is the integral square root of 81 u to the 2/3 plus 4 times 9 u to the negative 1/3, right? Because on the denominator. And so 1/2 dw would equal 9 u to the negative 1/3 du. Okay, and so I can replace all of this with dw, and this part here is the square root of w. So then we're integrating square root of w dw, And that's just, that's u to the 1/2, so add 1, w to the 3/2 over 3/2, which is 2/3 w to the 3/2. Now we got to do the bounds of the integral, and we have to go, well, x was 0 to 3, so that means u of 0 was 4. The u went from 4 to 7, right? U went from 4 to 7, and so w of 4 is 81 times 4 to the 2/3 plus 4. And w of 7 was 81 times 7 to the 2/3 plus 4. Okay, so then the numbers gets pretty ugly here in terms of the actual... yeah, I don't know. I would just sort of plug those in. So we're going to plug in from, you know, basically these expressions, 81 times 4 to the 2/3 plus 4 to 81 times 7 to the 2/3 plus 4. And whatever, it is going to be a super terrible number. This is 2/3 times 81 times 7 to the 2/3 plus 4 to the 3/2 minus 81 times 4 to the 2/3 plus 4 to the 3/2. And there's not really like a whole lot you could do to simplify. That's kind of a messy answer. You got to use your calculator at some point to do that, but that's how you could have analytically done that integral. And then here we have number 4, dy dx here. The derivative is 1 over secant x times the derivative of secant x, which is secant x tan x, right? And so that just equals tan x. And so we're going to be integrating the square root of 1 plus tan squared x dx from 0 to pi over 3, right? But 1 plus tan squared x is, you know, your trig identity. That's secant squared x. So it becomes integral from 0 to pi over 3 secant x. Now, secant's cosine, so this is technically absolute value, but in this domain, it's always positive, so I don't need to write the absolute values. I usually try to check, why do I not need to write the absolute values? And that's a good habit to get, to be precise. The integral of secant of x, if you don't know, is ln absolute value. I think this is right. Secant x plus tan x. And so we go from 0 to pi over 3. Natural log secant of pi over 3. Remember, secant's 1 over cosine. Cosine of pi over 3 is 1/2, so that's 2, plus tangent of pi over 3. Just get my unit circle to be here. Y over x. So tangent of pi over 3 is, it's taller. This is root 3. Secant of 0 is 1, because cosine of 0 is 1. Tangent of 0 is 0. Ln, this is just ln 1 is 0, so I just get ln 2 plus root 3. All right.